Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as ray optics. Let's start. Now, what do we understand by focal length? No, what do we understand by power of accommodation? What is power of accommodation? Now, the normal human eye can clearly see objects at a large distance without any difficulty. Why? Because the human eye is a natural lens which is fixed in its place by muscles. It has an ability to change the focal length very fast and to identify colors. This power of changing focal length is called as power of accommodation. By changing the focal length, you can see far off and close by objects easily. Okay, so the power of changing the focal length, the power of changing focal length is called power of accommodation. Next, what do we understand by DDV? DDV stands for distance of distinct vision, right? What does that mean? The minimum distance of an object from an unaided eye at which an object can be seen without causing any strain on the eye is called as distance of distinct vision. In order to see an object should be placed at a distance from the human eye. The minimum distance at which an object should be placed from the human eye so that it can be seen clearly by the human eye is called as distance of distinct vision. In the case of human eye, this is 25 centimeters. That means if you want to see any object clearly, it should be minimum placed at a distance of 25 centimeters from the human eye. Right? So what is DDV? The minimum distance of an object from the unaided eye at which the object can be seen without causing any strain, without causing any strain to the eye, is called distance of distinct vision. It's called distance of distinct vision. Right? It's abbreviated as DDV. Right? This distance is 25 centimeters for normal human eye. Right? That's called as DDV. Next, let's see a simple microscope. Let's see a simple microscope. Let's see the construction of a simple microscope. Right? Principal focus. This is the convex lens. This is the pole. Right? This is my principal focus. This is the principal axis. Principal axis, principal focus. The object is placed between P and F. Right, this is the object, say AB. You would have a ray of light passing straight and passing through the principal focus on the other side, and another object passing through another ray of light passing through the pole. This is how the ray of light will pass. As a result, you will get a virtual, magnified and erect image. This is my virtual, magnified and erect image that I will get, A1, B1. Right? Okay, so this is going to be this is how a simple microscope works. Let's assume that this angle here is beta. That is the angle subtended by the object on the eye is say beta. Fine, do we get this in here? Right, now let's start. Now what do we understand by I can say that let AB be the AB is the object kept within the focal length of the convex lens. AB is the object. I'll just give you the explanation of the diagram before I start with the derivation. AB is the object kept within the focal length. AB is the object kept within the focal length of a convex lens. Right? Next, A1, B1 is the image. Right? So I can say that image A1, B1 subtends an angle beta on the lens. Subtends an angle beta on the lens. Right? Now, I can also say that let the distance of distinct vision be denoted as D. Let D be equal to DDV. Instead of writing DDV, I'll be writing it as D. Right? Let alpha be the angle subtended by the object at the eye. Let alpha be the angle subtended. Let alpha be the angle subtended by the object at the eye. Alpha be the angle subtended by the object at the eye when the object is at DDV. These are all the assumptions I am making. I'll just show you this. Instead of placing the object between F and P, suppose if I place the object at DDV, right, from my pole, then let us assume that this angle is alpha. Alpha is the angle when the object is at DDV, beta is the angle when the object is between P and F. Okay. Then the ratio beta upon alpha, the ratio beta upon alpha gives the ability of the simple microscope to produce magnification. Gives ability of simple microscope to produce. Gives the ability of simple microscope to produce magnification of an object. Magnification of the object. Right, that is what is beta upon alpha, and this ratio is called as magnifying power. Right. So what is magnifying power? Magnifying power. Magnifying power of a simple microscope. Magnifying power of a simple microscope is defined as the ratio of the angle subtended subtended at the eye by the image to the angle subtended at the eye by the object. So this is your beta upon alpha is called as magnifying power, right? By the object if object placed at a distance of distinct vision. Right? That is what is magnifying power. So I'll write this now in terms of formula and it's shown to you. I can therefore say that magnifying power is angle subtended at the eye by the image to the angle subtended at the eye by the object, angle subtended at the eye by the object if it is at DDV. That's my formula for magnifying power. Therefore, I can say that magnifying power is nothing but beta upon alpha, right? Now, let's consider, I've shown you this diagram, drawing the diagram again. This angle was alpha, this was P, this was A, this was B and this was A. We've already drawn this diagram where this distance is D, right? Now, in that case, I can therefore say that what will be tan alpha? Tan alpha will be nothing but AB upon BP. Tan alpha will be nothing but opposite upon adjacent. Therefore, I can say that tan alpha is nothing but AB upon D. Similarly, from the simple microscope, I can also say that we have this also diagram wherein I have this is AB, this is A1, B1, this is P, and this angle we had assumed as beta on the simple microscope. I can say that tan beta can be written as A1B1 upon PB1. In this diagram, I can say tan beta is A1B1 upon PB1. Some of you will say that sir, tan beta is also AB upon BP. Either way, right? Now, since alpha and beta are very small angles, therefore tan alpha is approximately equal to alpha and tan beta is approximately equal to beta. Since alpha and beta are very small angles, in variance if two angles are very small, if an angle is very small, then the trigonometrical function of that angle is equal to the angle. Thus, I can say that alpha, therefore I can say that alpha is AB upon D, right? And I can also say that beta is A1 B1 upon P B1, which is also equal to, guys, look at this diagram. I can say this is also equal to AB upon BP. But what is BP? BP is the distance of the object from the lens. Distance of the object from the lens is written as U. Therefore, I can say beta is nothing but AB upon U. Now, we know that magnifying power is nothing but beta upon alpha. Beta is nothing but AB upon U divided by alpha. Alpha is nothing but AB upon D. AB gets cancelled. So this is going to be nothing but D upon U. So the magnifying power is going to be D upon U. But by Lensmaker's equation, for a convex lens, we know that 1 upon f is equal to 1 upon v minus 1 upon u. We've already derived this in your Lensmaker's equation. Now, as per sign convention, we know that u and v are both negative while as f is positive. U is negative for a convex lens, v is negative and f is positive. If I use the sign convention here, I will get this as 1 upon f is minus 1 upon v minus 1 upon u. I am applying the sign convention here, right? So therefore I can say that 1 upon f is minus 1 upon v plus 1 upon u. Therefore 1 upon u is 1 upon f plus 1 upon v multiplied by d. If I multiply by d, I will get d upon u is d upon f plus d upon v, right? But we know that d upon u is nothing but magnifying power. Therefore, I can say magnifying power for simple microscope is d upon f plus d upon v, right? So it is clear that the magnifying power of a simple microscope depends upon the image distance. F cannot be changed, D cannot be changed. The only variable there is the image distance, right? Now, let's consider case 1 on the basis of this formula. If image at infinity, if the image is at infinity, then I can say that V is infinity. Substitute the value of V as infinity, so I'll get therefore magnifying power is D upon F plus D upon infinity. But anything divided by infinity is 0. Therefore, I can say that magnifying power is D upon F plus 0. Thus, magnifying power of a simple microscope is D upon F if the image is formed at infinity. Case 2. If image at DDV, let's assume that the image is formed at DDV. If the image is formed at DDV, then I can say that V will be equal to D. Therefore, but magnifying power we know is D upon F plus D upon V. Therefore, I will get magnifying power is D upon F plus D upon D. Therefore, magnifying power will be D upon F plus 1. So, magnifying power of a simple microscope will be nothing but D upon F plus 1 if the image is formed at distance of distinct vision. This is your simple microscope. Next, let's start with compound microscope. Compound microscope, principal axis, right? You're going to have two lenses here. One is going to be your eyepiece and one is going to be your objective. This is your objective. The objective is smaller here. The object is placed in front of the objective, right? This is my objective. This is my object AB. Now see how the compound microscope works. One ray of light will pass straight and then after passing through the lens will get refracted the other will pass through the pole and will meet at a point. This will give me a real magnified and inverted image, which will be nothing but A1 B1. Now the next is your eyepiece. Now the eyepiece is going to be bigger than the objective. You would have a ray of light. See, I'll draw the arrowheads to show you how the ray of light moves. Right? One ray will go here and it will get refracted. The other will pass through the pole. And they will meet and you get a virtual image here. Virtual, erect and magnified with respect to this, right? So this is going to be your B2, A2. This is your objective, this is your eyepiece. Fine? Okay, now let's assume that this angle here is beta. Right? Okay. Now let's write our assumptions down. Let's assume that the magnifying power of a compound microscope. How do I define the magnifying power of a compound microscope? First, let's see the working here. This goes here. Right? I can say that AB is a small object placed. AB is small object placed. AB is small object placed just beyond the focus of the objective. The focus of the objective. So that's my object AB. I'm giving you the explanation of the diagram, guys. The objective forms a real magnified and inverted image. The objective forms a real inverted and magnified image A1 B1. So A1 B1 is going to be the image. Now the position of the eyepiece is adjusted. The position of the eyepiece is adjusted. The position of the eyepiece is adjusted such that the image A1 B1 lies within its focus. Within its focus. Fine. Now the eyepiece works like a simple microscope. The eyepiece works like a simple microscope. The eyepiece works like a simple microscope and produces final image. A2 B2. Fine. Okay. Now that was the working of the compound microscope. How do I define the magnifying power of the compound microscope? The magnifying power of compound microscope is defined as the ratio of the angle subtended. The ratio of the angle subtended. You've already seen this in simple microscope, so nothing new here. Subtended. The ratio of the angle subtended at the eye by the final image. At the eye by the final image to the angle subtended at the eye by the object. To the angle subtended at the object. Fine, do we get this in here? If the object is at DDV, if the object at distance of distinct vision, right? So it's the same thing that you had for simple microscope. Now let's define our angles. So I can say let beta is the angle subtended at the eyepiece by the final image. The angle subtended by the eyepiece angle subtended at the eyepiece by the final image A2 B2, right? Now I can say that beta is also the angle subtended by A1 B1. It is also the angle subtended by A1 B1 at the eye, right? Now let us assume that alpha is the angle subtended at the eye, angle subtended at the eye, angle subtended at the eye by the object if it is placed at DDV, right? Now as alpha and beta are very small, therefore I can say that tan alpha will approximately be equal to alpha and tan beta will approximately be equal to beta, right? Now beta can be written as now see you have this image like this. This is B1, A1, B2, A2 and this was beta, right? So I can therefore say that tan beta for this, for A2, B2, A1, B1 is the object, therefore I can say that tan beta is going to be nothing but A1, B1 upon U, because this is the distance of the object from the lens for A2, B2, and alpha is going to be the distance of the object when the object is placed at DDV, that's by definition. Also I can say that magnifying power is nothing but beta upon alpha by definition. So therefore I can say that magnifying power is nothing but beta A1 B1 upon U divided by AB upon D. So therefore I can say magnifying power for compound microscope is A1 B1 upon AB into D upon U, right? But what is A1 B1? A1 B1 is A1 B1 upon AB, that is height of the image upon height of the object, is nothing but magnifying power. Height of the image upon height of the object is magnifying power. We know that magnifying power, or not magnifying power, magnification. Magnification is also given by the formula V upon U. Now the problem is that there are two lenses. So this is for which lens? So this is for the objective, therefore V0 upon U0. So magnification is height of the image upon height of the object. Magnification is also distance of the image upon distance of the object, right? When this is with respect to the objective lens. Thus I can say that A1 V1 upon AB is nothing but V0 upon U0, right? Do we get this in here? So this is going to be this. Now magnifying power of the eyepiece from simple microscope, we know that I can also say that from simple microscope we know that magnifying power of the eyepiece is going to be d upon ue. In simple microscope we have derived this equation that magnifying power for a single lens for virtual image is nothing but d upon u for the eyepiece. The eyepiece is working like a simple microscope. Thus, I can say that the magnifying power of a compound microscope is, which is we just found out as A1B1 upon AB into D upon U, can be written as V0 upon U0 into D upon UE, right, which can also be written as magnifying power of the objective into magnifying power of the eyepiece, or magnification of the objective into magnification of the eyepiece. So that is the formula for magnifying power for compound microscope. Now, case 1. If final image at infinity, if the final image is formed at infinity, then magnifying power of the eyepiece, we have done this case in simple microscope. If the image is at infinity, then magnifying power is nothing but d upon f. So, and this is eyepiece, therefore fe, right? Therefore, I can say also we know that magnifying power is magnification of the objective into magnification of the eyepiece. So, which will be V0 upon U0 into D upon Fe. That will be the formula for magnifying power for compound microscope if the final image is formed at infinity. Right? Case 2. If the final image at DDV, if the final image is at DDV, magnifying power of the eyepiece from simple microscope we know is nothing but D upon F plus 1. Therefore, magnification or magnifying power is nothing but M0 into ME, objective into eyepiece. So this is going to be objective. Objective is V0 upon U0 into D upon F plus 1. That will be the magnification of a compound microscope if the image is formed at DDV. Also by Lensmaker's equation, Lensmaker's equation for objective. If I apply Lensmaker's equation for objective, I can say that 1 upon f0 is 1 upon v0 minus 1 upon u0, right? By Cartesian sign convention. Cartesian sign convention says that u0 is negative, right? Here in this case, since there is a real image, therefore v0 is positive. And for a convex lens, f is always positive. That's my sign convention. So if I apply the sign convention here, I will get 1 upon f0 is going to be 1 upon v0 minus 1 upon u0. So in which case I will get this as 1 upon f0 is 1 upon v0 plus 1 upon u0, right? Now if I multiply by u0, multiply by u0, so I will get u0 upon f0 is u0 upon v0 plus u0 upon u0, that is going to be 1. In which case I can say that u0 upon f0 minus 1 is u0 upon v0. So u0 minus f0 upon f0 is u0 upon v0 in which case I can say V0 upon U0 is F0 upon U0 minus F0. I am reciprocating. If I reciprocate, this is what I will get. Fine. So I've got the value of V0 upon U0. Now substitute this value. If I substitute this value, I will get this as substitute V0 upon U0 in case 1 and case 2. Case 2. So I can therefore say that case 3, if final image at infinity. We had found out that magnifying power is V0 upon U0 into D upon Fe, right? Which you have just found out is nothing but F0 upon U0 minus F0 into D upon Fe. So that will be the final image that will be the magnifying power of the compound microscope if the final image is at infinity. Case 4. If final image at DDV. From case 2 we know that magnifying power in that case will be V0 upon U0 D upon F plus 1. So this will be nothing but F0 upon U0 minus F0 into D upon F plus 1. So that will be your magnifying power of the compound microscope. Fine, do we get this in clear? Right, we will stop this here for the day. Thank you very much.